highlighted here, node number A and B. So you need to calculate the delay starting from source. Okay, source alert. So here comes the source. From source to A, what is the delay? From source to B, what is the delay? Can you calculate? Elmo delay model. So the path, whatever resistance comes in the path assigned, that only you have to take. Any additional resistance you need not to take. Only capacitance you have to take. Okay.
From source to A and source to B, right?
Yes. There you need to write two equations. One equation from source to A, another equation is from source to B. Whatever comes in the path assigned, those resistance only you have to take, nothing else. Okay, but capacitance you have to take if that particular node comes into picture. So you're done?
Yes, ma'am.
Let other complete. Yes, Harsha. Ready?
Yes, ma'am.
Ah. So what you're going to tell me now? Source to B or A?
Ma'am, I'll tell you both, ma'am. B is
Okay. So first we got
R1C1,
hmm, source to B.
R1C1, Yeah, so it's to be R1 C1.
Okay, TPD is going to be R1 C1.
Yeah, and then R1 into C2 plus C3.
R1 into C2 plus, yeah,
And then
R1.
yeah, and then R1 plus R6 into C6.
Why don't you consider all these nodes? Because C2 plus C3 you are considering the same node, right?
Oh, yeah.
We should consider C4 and C5 along with C2
Yeah.
and C3.
Yes.
Yes, ma'am.
C4,
Correct, correct.
C5. Okay.
All of them in summation. Yes, ma'am.
Okay. Then you have R1 plus R2 times, sorry, R6 times of what?
C6.
Okay.
Yes,
I
ma'am.
hope you got, right?
Yeah, yeah.
So now similarly S to A, please write all of you.
Should I tell, ma'am, or?
Yeah. Let me complete. Okay. So now S to A. Yeah. R1 C1. Then can you hear me?
Yes, ma'am.
Plus
R1.
R1 C6.
Okay. Plus
R1 plus R2 into C2 plus C3.
R2 into
C2
R1.
plus C3.
Yeah. Because for R3 you need not to consider, right?
Yes, ma'am. Plus R1 plus R2 plus R4 into C4.
Into C4 plus
R1 plus R2 plus R4 plus R5 into C5.
R4 plus R5 in times of C5. Yeah. I have reached to the corner. Okay. So done. Okay. I hope you understood this. Let us start with the regular MOS structure because that's what is more important. Why I have given all this regular RC network is only for the practice. Okay. Because directly teaching with respect to MOS structure is very hard. So I thought I'll give you some exercise first. Then let us take up the MOS structure. So now I'll be posting a circuit. I think you can see this. Are you able to see this?
Yes, ma'am.
Yeah. So what is this? The example is uh, 3-input NAND gate, and the size units reference is unit size inverter with the ratio. Inverter ratio is 2 2 bar 1. W by W by L of P by W by L of N is going to be 2 bar 1. Okay. So with respect to this, they have size. I think sizing we know already now. So now they have considered all the diffusion capacitances. Okay. So you have gate to source capacitance. I mean gate capacitance you have drain capacitance of every single MOSFET. Since it is bottom section is N MOSFET, it's connected with respect to ground because source is grounded, but the top section is P MOSFET is connected with respect to source. Source is connected to VDD, so it is connected to higher potential. And here where you have Y, at Y, the total switching, if you see, you have a 2C here, and a 2C here. So 6C plus another 2C to connect it to the output load. So at the output load, the total capacitance what you can see is 9C. Hold on, okay. I think you'll have a doubt here. Please analyze. There should be a doubt. I'll get back. Hello, can you hear me now? Uh, any doubt here?
Ma'am, we haven't taken the loading.
Load, yeah, anyways, load is not yet connected. Then we connect, let us take. That's okay. Apart from that.
Have they shorted all gates and all?
Huh? This
Like
is
the
ABC.
first
I mean,
PMOS, they've
I mean,
shorted to the gate of first NMOS here.
CMOS structure, no man. This
Ma'am,
is really
a
a silly
common A
question.
inputs basically.
ABC.
Okay, okay. Understood.
Okay. Apart from that, I was expecting one question, but you didn't ask me. Okay, clue is somewhere here. That question is expected. Can you guess
Okay, you're asking why is it 3C?
what it should be?
It should be 3C because they've written 3 over there. 3 as the ratio of the device.
That is for one device, right? There are two devices, right?
These
For one.
2C capacitances won't get added as in parallel with 3C because they are not connected to the same node, right? So
Which one?
it's correct, I
No,
guess.
no, no. See, there are in a series transistor, whatever given in the bottom section, a source of one is connected to the drain of one. So 3C will be added from the source of one device, but another 3C should be there, no, from the drain of another device. Did you get this?
Yes, ma'am.
So I should have taken 6C, no? Why I have taken 3C? I
Can you
think,
repeat? Can you please repeat, ma'am?
see, here the capacitance. So what capacity I'm representing here, 3C? Is it like I'll take, say, transistor number with the input C, okay, for example. If I'm
Mm-hmm.
taking that, this is the source capacitance I'm writing, right?
Ma'am, that is CDB, ma'am. That
C
capacitance 3C is CDB.
of second device,
No, of the device C.
of the C. D is somewhere here. See, D terminal is here. This should be source end, right?
Where are you marking, ma'am? My,
Uh,
no,
so this is source, right?
that is the source terminal, and D is above. Yeah.
That's a source terminal. But for the next device, transistor B, where is the
The
drain terminal?
the red
The
cross.
same red color marked one only. So that
Correct.
capacitor, where is that capacitance then?
That is the CDB of B.
Where is that?
3C, ma'am. The one that's right next to the device B.
Right next
The,
to, no, no, no. See, you look at this particular portion, okay? Only this highlighted one. You have two devices.
correct, ma'am.
One,
Oh, you're saying it should be 6C because there will be a contribution from C device and B device both.
yeah, see, one 3C will
Mm.
come as
Correct, ma'am.
this, and
Correct,
another
correct,
3C
ma'am.
should become, right?
Yes, ma'am.
Okay, this is how it should be. 3C, 3C. Okay, but here it's taken only like total at this particular node you are going to have 6C if you just look at the device. Okay, but we take here 3C. That's because selected or something. It is because of the fabrication. See, when you do layout, I thought you will ask this question to me. Okay, so when you do layout,
Sorry, ma'am. Next time.
next time, see, layout is like you understand, say it is a N MOSFET, okay? So N MOSFETs, I'm writing polysilicon for C, okay? For example, this is C, and you have a diffusion. I'm writing top view of a layout, okay? So this is diffusion, drain end of input C, I mean this particular device. And here comes the source end. See, now source of C input C device is connected to the drain of input B device. So it should be something like this. Drain, and you have a polysilicon for B, and there comes a source. Typically, this is how layouting will be done, okay? So these two are attached, okay? So, but what happens is like this source and drain, these two are shared, you know, shared in the sense this is n material, and this is also n material. Shared means you need not to actually create a two diffusion. Instead of having two diffusions, you can have single diffusion only while doing layout. Okay, you need not to create two since they are shared. So what happens effectively, you get to see only one capacitance. Okay, if it is like separate, and if you do additional contact to connect them, so then it will be like 3C plus 3C, 2 will come. So that time you have to take 6C. See, some of the reference, if you are referring, a few people take it as, still take it as 6C, few people take it as 3C, but according to our textbook reference, it is 3C. But why 3C is like due to the layout. So these two are like merged into one single structure where there is no bifurcation, the source and drain, because they are shared nodes. Okay, this will usually happen only in the series connected transistor, not in the parallel connected transistors. Okay.
Ma'am, I have a doubt.
Yeah.
Ma'am, won't this affect the mobility? Like, because this well is having a lot of n number of mobile carriers. Well, D and S are having relatively less, right? So won't it
It is
affect the
all
current or
about
something?
discharging, right? See, it is all about like NMOSFETs are responsible for discharging, right?
I'm
So
not talking about the capacitance. I'm talking about current in general, because the S and D, which is combined together, will have double the concentration of holes, electrons. Is it like that, or how? I didn't get that part.
it is like it's not double the concentration; it's the same concentration. If you make the concentration double, then it's not so. It's the same current. It's the same concentration.
So you're saying like
This
it's
is
like having
this
a
is like
common drain and source for both of these MOSFETs at the
yes,
same time
yes.
with the same
It's
width and
like instead of having them as a separate one, and you additionally connect them through a contact, you have it as a single slab of material. That's it.
so this N well is same as the N well above the C marking which you have done. It is same, or is it
It's not
different?
N well. C marking. This is a source. This particular diffusion is common for input C and input B.
And they are identical with respect to the drain of C and to the source of B.
Yes.
Completely.
Yes.
Okay. Fine.
Ma'am, can you please repeat the layout just once more? Quickly, ma'am, just once.
See layout, series layout. See, if you look at all these devices separately, okay? Let me take out. It should be something like this, right? And you connect these two devices through some additional contact. Yes or no? Because they are connected in series.
No, but don't we use a singular, like a single base, the body substrate?
But that is P, no man. So I'm speaking about N diffusion. It's a N MOSFET, right?
No, that's you're right, ma'am. But to design many ICs in that way, before we do all the things that has to be done, right?
See, I'll take to the another art. So I'm writing a cross-sectional view, okay? So this is what you are speaking about, the wafer P substrate. Yes? Yes, yes. Sorry,
Yes,
Harsh.
ma'am. Yes,
Yeah.
ma'am.
So I'm writing. So this is the part for say input C. Okay.
Okay, ma'am.
So this is what you have for input
B.
B. See one diffusion. This is a drain. This is done.
Yeah.
So you are going to have shared diffusion for
In between.
In between, because they are connected.
Okay.
Got?
So you're saying it's just the same thing, nothing different.
It's the same thing. We don't even change the dimension. See, if you change the dimension, what will happen is like width of diffusion will increase, no? So capacitance once again will increase. So it's all depends on what is the width you take. See, if you take, see, you combine it and you take double the width, then you have to take 6C. It is, these are all the tricks they follow to reduce, all parasitic capacitance. Still, they have all that.
Like now that you brought the point of like changing the width of that N well,
Mm.
won't it
Not,
matter?
it's not
Because
N well, man. It's diffusion. It's diffusion.
okay, sorry, ma'am. Diffusion in the P substrate, the N plus diffusion in the P substrate,
Mm.
we try to evaluate the resistance that is going to come in that series path,
No,
and we
no.
want that resistance to be R. Like that's how we try to define our W by
Yeah,
L.
that will be always there. So when we have
Correct.
all these in
So
series, we are trying to represent, see to it that total resistance is R.
yes, ma'am. So now that we've made two regions common,
Mm.
won't that calculation be affected?
No.
It won't be, ma'am.
Mm-hmm. They are shared. See, it's like it's like since they are connected in series. If you want to discharge some current, okay, so all should be on. That is a condition.
Yeah, yeah,
If one on another off, there is no point. There is no current
correct,
flow at
ma'am.
all. That's
Correct,
why.
ma'am.
That's why. Okay. So that's the reason. Anyways, if you have further doubt, let us discuss later. Else, I'll end up taking additional class.
Yes, ma'am.
So
Yes, ma'am.
that's how we actually take 3C, 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 and this is a typical setup. Okay. So this is an example of three input NAND gate, and somebody asks you to calculate what will be the worst case propagation delay in this. Okay, one question: worst case propagation delay. Worst case means what? You all already know. Worst case means what? In the PMOS side, at least one device is on. Worst case. If all three are on, because then charging will be too fast. Okay. So worst case is like only one PMOS is on. That's the worst case. While discharging, worst case if you want to measure, like all the devices should be on, okay, because they are all in series. It's a typical setup, right? So how do we actually calculate? So let us analyze on that. So suppose, I think I have already have this, have taken, it will be good else. Yeah, can you see this? Anyways, it's better to write. No, I'll write it again. Don't worry. So now there is one single NAND 3 gate. So I'm supposed to calculate the worst case delay. Worst case means what? PMOS, only one device is on. So you may get to see, because there are three inputs A, B, C. So you get combinations like 101, okay, or the combination like 011. You get to see all these combinations, right? Because it's a NOT gate. So whenever you have such combination where only one PMOS is on, that time you call it as a worst case. But when you want to calculate corresponding delays, look how it will be. Okay, so let me rewrite the circuit once again. So worst case. So should I draw MOSFET again? No, right? I think you might have copied.
Yes, ma'am, it's fine.
Okay. So you have R, because only one device must be on, rest all off. Okay. So the total resistance what you see at the pull up is R. So what was the total capacitance you could see at the switching? You had around 9C capacitance. Okay. Okay. So this is without considering any load, you had this particular setup. Now the discharge. Say for example, now what I said, like only one device will be on. 0, 0, I mean 101, 011. So that means what? There is a bright chance that, say if I consider inputs are like A, B, C, and if I make sure that, say BC, option is 0, 1, 1, so that means A, B, C. A is 0, but BC are 1. So A is 0, BC are 1, 1. So corresponding to A, one device, this will be on, but these two devices off. So you have one resistance, what you can see from this, I mean PMOS section. But what will happen, since B and C both are on, you can see these two devices are on, right? Yes or no? When I say the worst case, worst case means only one PMOS device is on and other two off. That means what? You are making two NMOS devices on. Yes or no, students? Yeah. So that means what? You cannot say take out the NMOS section from this at all. So that means what? You need to include them. So imagine there are two devices, device number C and device number B, both are on. So what should be the effective resistance? The width you have taken as 3 times, right? 3. So that means the resistance is R by 3 here, R by 3 here, but the last device is off anyways. So now what you have here is 3C capacitance as we discussed. So there is a 3C capacitance here. Say let me call this as at node 1, and here also comes a 3C capacitance. 3C capacitance at node 2, but the last device is anyways off, so we will not be bothered. But why? Because the input condition ABC, I've taken worst case where A is 0, BC both are 1, 1. So this is the only case where I can say both the devices are on, B and C both are on. Say if I get a condition that for example 101, that time I need not to consider bottom transistor. You know why? Can you tell me why?
Can you repeat the question? 101, ma'am?
Because the middle transistor is already off.
Off. Yeah. So if the input condition given is 101, then I need not to bother about additional resistance and capacitance in the pull down section. That's because B is off, right? So that comes in between. So there won't be any discharge. Path is not complete. But what happens if the input condition is 0, 1, 1? That's why I took it as a worst case. If it is 0, 1, 1, what will happen? A B device is on, C device is also on, so it can add some additional capacitances because path is complete till this particular point. Got the point? Because output is connected here, this is connected load, right? All these capacitances are switching type, so I think we have to consider. Okay, so if this is a case that one single device, so you want me to connect the load now? Shall I? So you got the concept, students. If any doubt, please ask me now only. So I have considered 3 input NAND gate, and the worst case is like the input ABC I have taken as a 0, 1, 1, where A is 0, B1, C1, and where is A, B, C, everything is given according to this particular diagram. Okay. So when I say A is equal to 0, the bottom transistor in a NMOS is off, but top 2, right? BC both are 1, 1. Since 1, 1, NMOS will still be on. So I'm actually charging the device because PMOSFET A0. So this particular device is on. It is trying to charge the load, but meantime, there are 2 devices which can try to discharge also, because these 2 are on, they are not off completely. Got the point? So that's why when I write RC equivalent, I'm writing in this way.
From 9C, how much? I didn't get that.
9C is, I think last class also we calculated C contribution at the node, how much is the total capacitance? 2C, 2C, 2C. Okay, 6C plus from the bottom 3C is added. How much? You have 2C, 2C, 2C and 3C, 9C.
You're adding only one 3C capacitance from the bottom.
Because only one particular device, the drain capacitance is connected, right? Because
Okay,
they are all in series. If
to the
they would
node.
have been
Okay.
in parallel, then you would have added
Okay.
additional. Yeah.
ಮ್ಯಾಮ್
So, yeah.
ಮ್ಯಾಮ್ 2C ಅದೆಲ್ಲ ಆಡ್ ಮಾಡೋದಕ್ಕೆ ಎಲ್ಲ ಪ್ಯಾರಲಲ್ ಆಗಿರ್ಬೇಕಲ್ವಾ? ಬಟ್ 3C ಅನದರ್ ಟರ್ಮಿನಲ್ ಗ್ರೌಂಡ್ ಇದೆ ಅಲ್ವಾ?
It is a drain capacitance, no? It can still hold a charge.
ಎಸ್ ಮ್ಯಾಮ್, ಬಟ್ ನೀವು ಡೈರೆಕ್ಟ್ ಆಗಿ ಎಲ್ಲ ಆಡ್ ಮಾಡಿ 9C ಮಾಡ್ಬೇಕಂದ್ರೆ ಆಲ್ ಶುಡ್ ಬಿ ಇನ್ ಪ್ಯಾರಲಲ್. ಬಟ್
see, this is a parallel connection only, man.
all 2C are in parallel. I agree with that. But 3C isn't parallel with the 2C, ma'am.
Okay, at this node, how many capacitance? This is a node capacitance, right? You have 3C.
Yes, ma'am.
Then another column 2C.
That you can directly write as 6C, no problem.
6C. Parallel only, man. These two are parallel.
Ma'am, at that node, 3C is connected to ground, while the 2Cs are connected to VDD. Will that make a difference or?
See, 2C connected with this is P MOSFET, no man. This will hold the charge. This is source, right? P MOSFET. This will see. This is a discharge nodes. They are all discharge nodes. These are all like charge nodes. So this charge will be always there because they are directly connected to VDD.
Ma'am, capacitor will hold charge when there's a potential difference between the two plates, right?
See, internal capacitance, there is something like a built-in, I think MOS structure, if you recall, all diffusion capacitance. There is some intrinsic capacitance formation always, right? There will be some capacitance hold in the diffusion, if you recall.
That I understand, ma'am. We are taking these capacitance separately for drain, source, and gate because of the assumption that she made in the first class, saying we'll take effective R and effective C. Now my question is, at the drain of the PMOS, you're connecting 2C to the VDD, and at the drain of the NMOS, you're connecting 3C to ground. Now, how are you considering both of them to be in parallel? That's my question.
See, how to answer? See, these N MOSFETs, okay, sometime P MOSFET, gate is not at one single, I mean, constant value. It is a switching type, right? Every time. Because it's all about input. I mean, P MOSFETs are all switching type. It's not like idle condition, right? You got my question? I mean, see, what is the input here? Say when I say worst case, you consider only this device is on, these two are off. So this potential changes here. This will go 1, right?
I didn't get you, ma'am.
See, when
okay,
I say
when these two are off, yeah, correct. When you're giving 1 to
so that means
B and C,
every time that 2C value, it need not be charged to the high, but that value will be always changing type, right? With respect to input.
Still not clear, ma'am.
See, switching means what, man? See, the switching capacitance means value of these capacitances will change based on the input given.
Correct, ma'am.
Okay, the maximum is 2C. I'm considering the worst case. I'm considering the maximum. I don't know exactly it is fully charged to 2C or little less. I don't know. Okay, because C value I have not defined. The maximum it can go up to 2C value because for a technology, what will be the maximum value C, that has to be defined. Okay.
Ma'am,
So
that is fine. I understood that part. You're considering 2C as a worst case, so that is fine. My question is, when you're doing these Elmos delay, all the capacitances are either grounded, so it's easy for us to consider them in parallel.
What?
But here, 1 or 3C is connected to ground, while 2C is connected to VDD, ma'am, for the PMOS capacitances. Can you see the drain capacitances?
Yeah. Drain capacitance.
So, yeah, ma'am. So, how are you considering them in parallel? Like in small signal analysis, we considered virtual ground. So, we said 2C and 2C can be in parallel. But here, how are we doing? Is my question. The same concept of.
Okay. Have you heard of Miller capacitance?
Yeah, ma'am.
What is the concept?
The concept is you're dividing the capacitance between the input and the output depending upon your gain. Yeah, you're splitting the capacitance between nodes, right?
So
yeah.
There is some analysis based on that. So you can still take all these capacitances in parallel. Okay. So I think if further doubt, we'll solve this, keep these doubts for the tomorrow class, right? Because it's already okay. So it is like all 9C total 9C, because once again I have not considered the load, because let us first understand how do we actually calculate the delay. Once we calculate the delay, let us analyze on the rest. Okay. So now say I try to connect a load. Okay. So load means what? A fan out, right? How many such devices I want to connect. Okay. So fan out, if I am considering, say, let me take fan out as some H value. This defines how many load devices. Okay. So ideal load condition means what? Fan out of 1. So that means H is equal to 1, then ideal. Okay. So similarly, you can have H is equal to 2, whatever. So we actually do this analysis typically for identical loads. Identical load means if you have considered NAND 3 as a driver input, so then you have to consider NAND 3 only as a load also. So then it's identical load. Okay. So for H identical device. So now that means what? Identical means what? If I look at this circuit diagram, at the output, I'm going to have one more such NAND gate. Okay, this might be connected to one of the inputs of the next NAND gate. So one to the PMOS. Okay, similarly, you can have few more gates, devices, few more devices. But this output will be connected to the one of the MOSFETs in N section and the P section. So this is what is the meaning of like connecting, right? So now from 1, so you get a 3C, in the top section you get around 2C capacitance, but from the bottom section, what is the capacitance? Gate capacitance, what is seen? 3C, right? So what is the total capacitance you
5C.
see at 5C? Okay. So that means if you connect one particular load device, from one device, the load capacitance asserted is 5C. Okay. So now when I'm saying I'm going to connect a load, then what will happen is like additional capacitance will be added. So one device, then 5C capacitance. So if H device, that means if I am connecting H identical loads, then
it's H times 5.
So then it is H times 5C. Okay. So that means, say, let me imagine that I'm connecting H load. So let me be little general. So what will happen if I connect H identical nodes? So what will happen to the total capacitance seen at the output? It is 9 from the driver plus H5 times of C will be the total capacitance what you can observe at the Y node. Okay, connecting load condition. So this is the total capacitance what you can see for a 3 input NAND gate with identical load connected. Say if I say load is not identical to the output of NAND, I'm connecting a NOT gate, then NOT gate means what? What is the capacitance, input capacitance for a NOT gate with 2:1 ratio? 3C, right?
Yes, ma'am. 3C.
3C. So then it would be 9C plus 3C. Okay, it depends on what load you have connected. Okay. So total capacitance now, that means the current which is flowing, it has to charge all these. Okay. So now we are going to write propagation delay. So now this becomes your source, and what is the node of consideration? Because the node of consideration must be some at this point only. So this is the ith node. I want to I have to consider the propagation delay starting from source to the ith node, but how do I write? Using Elmos delay. Can you write? So this time this is going to be propagation delay rise time because I'm charging the capacitors. So can you tell me how do I calculate? Recall the Elmos delay model.
You'll have R into 9
R,
plus 5H into
okay.
C.
Okay, R into 9 plus 5H into C. That's all total capacity.
Ma'am, you can replace 9 plus 5HC as CL. That'll be easy.
No, it should be there, okay? Because
As
CL you
CL as
can
in just a
write.
notation. Just a
That's the
notation.
notation. But actually
Okay, fine.
CL means
R into
okay,
R into
R
9
into
plus
9 plus
5H.
H5 or 9 plus H5C, then
And the 3C is capacitance.
so
Treason.
though these two resistors are not in the path, but these capacitances you have to consider because so when you calculate TPD, this time it's a rise time. That is why it's rise time, because you are charging the capacitor. So it is going to be R times 9 plus H5. H is the fan out, C plus once again R times, because I have to take with reference to the source resistor, R times 3C plus R times 3C. Okay, so I have considered this and this. So this is going to be the rise time. If you solve this, what you will get? You get 15 plus 5H times RC. Okay, so in a simple anything you can write, no problem. TPD rise time. Okay, this is the rise time of NAND 3 with respect to the given input. So I have considered the worst case input where one of the input is off and other two on. So especially one of the input means the bottommost input with the bottommost transistor is off, rest all on with respect to NMOS section. Then you will get this. If any other combination, then the story is different. Okay. So this is the rise time. So if
Isn't it R plus R by 3 into 3C?
why R by 3? Because now look at this. What is the path? VDD to I, right?
Yes, ma'am. We did Y.
So where R by 3 comes there? In the path is assumed you have to take all the resistors, right?
But according to Elmore's delay, you have to consider even the resistors along the path.
It's not in the path, I'm telling, right? My path is only R to I, charging path.
Okay.
These are our additional parasitics.
Yes,
if you recall the previous C, look at this. If I want to consider from S to A, C3, R3 I'll not be considering because it's not in the path.
Yes, ma'am. Understood. Okay.
Okay. Similarly, the worst case fall time. Let us calculate. If while fall time or fall delay. So that is TPDF. So what will be the worst case? Fall delay. So that means what? If I want to calculate what is the fault time, I have to make sure that all these NMOSs should be on. If all these are on, then only I can calculate worst case. So here in this particular scenario where 0, 1, 1, there is no fault time. You cannot directly calculate the fault time because what happens. There is no VDD to ground because one device is off. You can't consider this as a worst case. So all the devices should be on. That's how you do even sizing, right? So if it's a worst case, then you have to make sure that all bottom transistors are on. See, I'm again and again telling you, I'm considering the worst case and I'm solving this. If you get a condition like input condition is say something like 011 or 101, then accordingly you have to write, okay? So now if it is a fault time, if I make sure that all NMOS, worst case, all NMOS devices on. So if that is the case, so the circuit looks like, so you have Y node, then I'll take all the capacitance like 9 plus 5, I consider the load also 5H times of C, then what is there? R by 3, you have 3C, then once again R by 3, you have 3C, then you have once again R by 3. The last 3C you need not to consider. You know why?
Because you have to start from there. There is no resistance behind that capacitor.
Yes. So last one you need not to consider. Okay. So this is how the circuit looks like, and what is the fault time? TPD fault. So now the source node is which one? So from ground here I have to consider. Okay, from here to this point. This point. Can you tell me what is the fault time?
My first term will be RC because R by 3 into 3C.
R by 3 into 3C. Let us write is complete. I'm considering these two now. R by 3 into 3C. Next
then
R by 3.
2R by 3 plus R by 3 into 3C.
R by 3 plus R by 3 into 3C.
Then
plus
3 times R by 3.
Okay, R by 3 plus R by 3
into the output capacitance, that is 9 plus 5HC.
So, are you clear, students? So, if you solve this, you are going to get it as 12 5H times of RC. So, this is going to be worst case TPD fault. So, fault time when you are considering your source, so node becomes like it's from ground, ground is a reference, but rise time when you are considering VDD is a reference. Okay, please note that. So, any doubt, students?
Ma'am, previous problem, when you had told that source to I is the path, then why to consider the capacitances there? Like previous problem.
Okay. This problem?
Yes, ma'am. Here you neglected R by 3, but you considered the capacitances along with it.
Because what is the path? Source to I is what? Now path is what? Source is VDD. I is where? In the output term.
Output, yes.
But this is a shared node, right? You have a node shared. That's why I gave this kind of structure. If I recall this, for example, this is source to A. If you want to calculate, okay?
Yes.
So how do you write? R1C1.
R1C1.
But when you come to this point, do you ignore C6? You will not, right?
No, ma'am.
So it's R1. So that's what I did for this case.
Okay.
Okay, na?
Yes,
Same concept.
Yes, ma'am. Yes.
Okay, any other doubts, students?
Ma'am,
Ah,
you told that if they mention the input like we have to take it as 0, 1, 0 or something
okay.
like that, then how to calculate the fall time?
Okay. So shall I give one question?
Yes, ma'am.
Okay. The question is, say take a question, okay? Take a question. So there is a switching of say 3 input NAND, okay? So 3 input NAND, which constantly switches, right? Okay. So 3 input NAND. So initial condition is 1 1 1. Okay, A B C are switching to 1 1 1. Then after that, say imagine it changes to 0, 1, 0. Okay, ABC I'll give you where it is placed. Okay, then once again it tries to switch to 1, 1, 1. So let us identify what happens to the rise time and fall time. So once again I'll be writing. So this time it sometimes I can.
For 1, 1, 1, you don't need to write it again.
No. No, ABC I'll write like placement of ABC because that matters. No, where is A, where is B, where is C? Okay.
Ma'am, it wouldn't actually because the second case is 0, 1, 0. So it will be the middle transistor that will be on.
Yeah, it's not actually required. Anyway. Okay. Anyways. Okay, can you try this? Rise time you try to calculate. Please write the equivalent model. See, imagine first, first is like, it is at the condition 1, 1, 1. So all the top transistors are off. So that means whatever is the charge stored in the output node and the internal capacitance, that will definitely discharge because all the transistors at the bottom off are on, right? So all the condition, what condition it says like all will be discharged, all internal nodes will be discharged. Okay. Now it is like shifting to 0, 1, 0. So why we have given this condition like 1, 1, 1, initially it will be 1, 1, 1 to tell you that all the internal capacitances are discharged, because what happens when A, B, C all are turning on, what happens like whatever is stored at the output node, whatever is stored at output node and at the internal capacitance, everything will be discharged to 0. Okay, it's done. So now new charging will happen when it is shifted to 0, 1, 0. Here where you have to start the analysis. Okay, so initial condition this is given only because to tell you that like everything is discharged now. Okay, so now 0, 1, 0. So now 0, 1, 0. Here where you have to start. So please calculate what is the rise time. I mean propagation delay for rise and propagation delay for fall for this condition. So it is raised, I mean 0, 1, 0 it has happened. Then after that, after rising what will happen? That you have to measure like is there any discharge, because only one device in the middle it's on, so there won't be any internal capacitance seen from the N MOSFET side. Okay, so now the input changes to 1, 1, 1, then you will write all the discharge path because there will be already charge in the output node, that's because of 0, 1, 0. Did you get this question? Students?
Yes, ma'am.
Please calculate.
Ma'am, one conceptual doubt. You said we apply 1, 1, 1 initially to ensure that our capacitances are discharged. so that we know the state of the system before we do anything with it. Correct?
Yeah.
So this capacitance that you're referring, is it all capacitances or just the load capacitance?
All capacitance. Imagine everything is discharged. Okay, because
so even the parasitics will get discharged.
Everything, because like you may, because since it is a switching type, you never know. Like sometimes due to previous switching, it will still all these internal capacitances can hold some charge, right? Because of previous conditions. So it's like we are giving you an ideal condition and we are telling you that okay, all capacitance are discharged, and the load condition I didn't give. So it's a 3-input NAND, but now connected as an input to a single NOT gate. Yeah, please write. Who, Harshita, you asked this question?
Yes, ma'am.
So try. The first case, like, anyways, 111 is the initial condition. Now 010, like 2 P MOSFETs will be on. So from top section, you get to see 2 resistors on, right? R in parallel R. So what is the effective resistance in the PMOS section? R by 2. Okay. So now R by 2, so what you get here, the total capacitance, it's only one single node is connected at the, to the, load. So you have 9C, as usual, this is 2C, 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 and this is 3C, so it's 9C plus, so this is what is inverter, right? In inverter, the input gate capacitance is 3C. So total load capacitance, what you can see, CL is 9C plus 3C. So what is the charging time? TPDR. I think directly you can write TPDR because 010. So that means this is 0, this is 1, 0. So since this is 0, there is no capacitance here, there is no charge. This is off, right? Yes, students. So according to
so all the transistors you can neglect.
All the capacitance below you can neglect. So it is R by 2 and the top. So you have VDD here and load capacitance 3C below. These are all off. So what model TPDR is just going to be R by 2 times of 12C. Correct? That's it. Yes, students.
Yes, ma'am.
Okay, done. So now what happens? There is no charging at the internal node because this condition was off. There is no charging at all. Okay, nothing is stored in the internal capacitance because this is off. Now immediately, here I hold a charge of 9C plus 3C. Okay, immediately it is now shifted to 1, 1, 1. So it's all discharge path. So will there be any capacitance seen in the internal node? What do you think? Because 111, is there any charging time or it is like a discharge only? Because path is complete now. What? All these capacitance will come into picture or not? What do you think?
It will come into picture.
Why? How?
Ma'am, it won't, ma'am, because the first transistor itself is off.
No, first case transistor was off. There is no capacitance charged at all, right? Internal node. Now it's like I'm looking at the condition where 0102, I am changing to 111 again. Okay. So now what will happen when this becomes 111? It is only the discharge. Because all these internal nodes, like, see, delay will be associated when, you get to see like some capacitance discharges like this. Then only all is like in the previous case, all these capacitance delay will come into picture, but there is nothing to discharge, right? Because they are not charged at all. It has to discharge when 111 condition is asserted. That condition is only 9C plus 3C. But in the previous example, what I have taken the general case. So this case is different, okay? Because worst case when I took, it was like two devices. Previous case. Okay, this case, two devices were on. So that means when output to node is charged, it is meantime charging. It means that meantime charging 3C from NMOS 1 and NMOS 2. Got the point? That's why we will consider that, because it takes some charge there. Okay, but in this case, during charging, the internal capacitances are not at all charged, because in the bottom everything is off. So what to discharge?
Another small doubt. Ma'am, when 9C plus 3C is discharging, the capacitors which are present at the NMOS are off, which means like they have no charge, right? So
they have no
essentially,
charge.
yeah. So
only
at T is equal to,
will come.
Yeah, only resistors are there. So what we learned in networks is at T is equal to 0, capacitors act as short circuits. So they allow charges to pass through them completely. The charges won't pass through the resistor initially, but they pass through the capacitors here. So these capacitors will get charged, and then after a long time, they will also start discharging. So
but whatever it is, you will be ultimately discharging this charge only, right?
Yeah, but time it will take will be different, no, ma'am, because it's different from only one capacitor completely discharging.
First of all, it is not exact, accurate, one single model. This is an approximation given by Elmore, right? It's not regular RC, delay calculation. It's an approximated one. He approximated this condition to be like this. It's not exact. See, when you do the RC simulation and when you manually calculate Elmore, see, there are cases like it may match, but it's not like it's exact.
Ma'am, how close does this model get to the practical case, like in terms of percentage, let us say?
This is helpful only for hand calculation, ma'am.
So in practical case, it will be a little bit more different. That's what I'm saying.
Yeah, you have to run. See, like RC delay model we did right yesterday when we started. Like we get second order system, third order system, and all, right? That's how we have to design a simulator to extract all RC network and run timing analysis on that. Elmore's why he has proposed this is to help us to do hand calculation easily, an approximated delay one. Okay, and since and one more important part what we have anyways in RC delay we do inverter, correct? So inverter is being the reference, right? So if we analyze what is the total delay in one single inverter, then so compared to inverter, say if I compare inverter and a NAND gate, how much extra effort a NAND gate should put to charge the output node to the same value? Or it's like how much extra a NAND gate should put to deliver same current as that of inverter. Okay, so we start analyzing the delay, like we'll compare every time delay with the inverter delay. So that type of analysis, so what we are going to do, that's what is known as linear delay model, and which is very promising. And you will wonder like how it is matching. Okay, so that linear delay model is actually, it is exactly matching to the RC delay models. Okay, but Elmore is like he is given one approximated, simplified, hand calculation model. That's it. So you got these students with the different input. Students, you got with the different input. So in exam, don't think that we'll ask only a worst case. We'll give all these input conditions, and you have to actually analyze. Okay.
So what will be the circuit, ma'am? Like when this happens, when you move to 111.
Huh?
When you go from 010 to 010 to 111, how will the circuit be, ma'am? Like the Elmore circuit.
This is the Elmore circuit. Okay. Because see, internal nodes they have not charged, right? It's only the discharge path.
Yeah, the circuit is correct, ma'am. Yes, ma'am. Thank you, ma'am.
So it depends on what input you give. Okay. So what I'll do, students, I am not taking extra class today. I will pose some examples, okay, or so, I mean problems in the group. You try to solve it by your own, okay? Is that fine? Yeah, yes, no, okay. And the reference material, I think one PDF which I have sent, that is sufficient for all this delay calculation, okay? That's more than sufficient. And if you just stick on to the textbook, definitely it is going to be very hard. So stick on to the material which I have sent as a PDF. And please, especially for the first unit, try to solve for all those fundamental physics, solved examples from the textbook. Solved example from the textbook, okay? All solved example. Please work it out, okay? That's important. Then comes all the theory in the first unit. Then what you have, CMOS circuits, AOI, OAI, then the transmission gate, strong zero weak one concept, then region of operations of CMOS inverters under different given condition. What if VDD is 5 volt and VTP is 1 volt? What if its VDD is 3 volt and VTP is 0.5 volt? Like that. Like we'll try to give different conditions. Then how we are going to solve? You try to practice that. Then how do you calculate switching threshold? Like you have to equate current and you can get switching threshold voltage. Then when the case that switching threshold is exactly VDD by 2, beta P to beta N ratios. Then what else you have? All these. Then what else, man? First unit. That's it, right?
Non-ideal effects.
Non-ideal, all theory part is important. Associated, see, you go through the textbook. For every non-ideal theory part, there is one solved example. Please practice that solved example, okay? That I didn't do actually, so you have to practice, okay? So apart from that, from the second unit, definitely delay, then the sizing. Elmore delay is more important because we are not doing regular RC delay, right? So approximated Elmore RC delay we are doing. So Elmore delay with all these rise time, fall time. I'll try to give you few more examples in the next class, and meantime I'll even post it in the group so you can try solving. And I think in the notes end we have covered almost all possibility for Elmore delay calculation. So you can refer to the material also. Have you ever opened that PDF? No?
Yes, ma'am.
Yeah.
Yes,
So
ma'am.
please refer to that material. So I think that should be sufficient for your test. Okay. Okay. Tomorrow let us continue. Yes, students. Bye bye then. It's time.
Thank you, ma'am.
Yes. Thank you, ma'am.
Okay. Bye.